Some of the most important ideas we have in mathematics are the concepts of relations, and specifically equivalence relations, and partitions. And at first glance, these two ideas are not going to look completely related, but we're going to see that they are in fact quite related, and we're going to take advantage of that throughout the course. So let's start with relations. So definition 1. Let's let S be a set. A relation R on S is a subset of S cross S, the Cartesian product of S and S. Remember that this set is the set of all x and y where x and y belong to S, so the set of all ordered pairs x and y. So a relation R is a subset of these. So it's going to contain some pairs where some pairs x, y, where x and y come from S, and it might not contain certain other pairs. Now, if a certain pair belongs to R, then we write x, R, y. And we'll see that this actually matches what we're used to in a second when we look at some specific examples. And then if x, y, the pair does not belong to R, we write x and y are not related. So this notation xry should be read as x is related to y using the relation R, and x not ry means x is not related to y under the relation R. Now, we can describe these relations in lots of different ways, describe it in words, describe it using a formula or some other condition. And we don't always need to use the symbol R. We'll use lots of different symbols. So let's look at a few examples. So let's, for all these examples that we're about to do, we'll let S be the set of all real numbers. So we could look at the particular subset of S cross S to be the set of all x comma y, where x is less than y. This is a subset of S cross S. And this is actually something we're familiar with. This is the relation less than that we're very familiar with. So this is because x, y is in this relation if and only if x is less than y. And so here's where our notation of putting the relation symbol in between two elements comes from. So less than is a relation because it describes relationship between two elements of a set. Equality is one also. We can define lots of others. We could define another one. One that we're not as familiar with. So we could say something like, let x twiddle y. So this twiddle or this tilde is also commonly used when talking about relations, when we want to define a relation that's not one that we're familiar with. So let x twiddle y if and only if x plus 2y is less than or equal to 5. So this is not a relation that we are too familiar with. So notice that we have that 1 is related to 3, 1 is not related to 3, since 1 plus 2 times 3 is not less than or equal to 5. But 3 is related to 1, since 3 plus 2 times 1 is less than or equal to 5. So we have that 1 is not related to 3, but 3 is related to 1, sort of like how 2 is less than 3, but 3 is not less than 2. So these two examples that we have here are not symmetric. They depend on the order that you write things down. But that's not true of all relations. If we look at the relation of equality, then the order that we write things down doesn't matter. If I write that x equals y, that's exactly the same statement as saying that y equals x. And equality has some other very useful properties in terms of these relations. And we want to define a special kind of relation that we would like to work with that behaves in similar ways to equality. So this gets us to our second definition. A relation R is called an equivalence relation if it satisfies the following three conditions. If it satisfies reflexivity, which means that for all x in the underlying set, x is related to x. Now, as we go through these, let's think about why this holds for equality, because equality is our gold standard for what an equivalence relation is. This is how we want to think about it. And for any real number x, x is in fact equal to x. And therefore, we say that equality is reflexive, or equality satisfies reflexivity. So that's one of the things that we want out of an equivalence relation. The next is symmetry, which says that if x is related to y, then y is related to x. So a symmetric relation doesn't depend on the order that you write down the two elements that you're trying to relate to one another. So if x is related to y, then y is related to x. This is true of equality, as I mentioned a couple minutes ago. And finally, we have transitivity, or we would say that the relation R is transitive. This says if x is related to y and y is related to x, then and y is related to z, I should say. If x is related to y and y is related to z, then x is related to z. We would interpret this in the case of equality as saying that if x equals y and y equals z, then x equals z. And this is true. This is something that we're familiar with. If you've got a string of equalities, then the element at the beginning of that string of equalities is equal to the element at the end of that string of equalities. That's just using the transitivity of equality. And so for any relation that we write down, we can try and determine whether that relation is reflexive, symmetric, transitive, etc. And so, for instance, the relation equality is reflexive, symmetric, and transitive. And hence, it is an equivalence relation. On the other hand, less than, the relation that we looked at first last time, is non-reflexive. And that's because a number is not less than itself. 5 is not less than 5. And to show non-reflexivity, you only need to show that we don't have some element related to itself for some element in your set, because reflexivity is a statement that says for all x in your set, x is related to x. So less than is non-reflexive. It's also non-symmetric, because if x is less than y, it could be the case that y is not less than x. So x being less than y does not imply that y is less than x. So it's non-reflexive, non-symmetric, but it is transitive. So we've got an example here of a relation that satisfies only one of these three conditions. And you can go through and it's an interesting exercise to come up with examples of relations that satisfy some subset of these. So coming up with relations that satisfy all three of these conditions means coming up with equivalence relations, and equality is our, as I say, gold standard for this one, but we're going to see that it's not the only one. And we've got an example here which is not reflexive, not symmetric, but is transitive. You could try and come up with ones that are reflexive and symmetric, but not transitive. Symmetric and transitive, but not reflexive, etc., etc. So we can go through and work on things like this. Now I want to point out something that we need to be careful of. Let's look at the tilde relation from last time. So remember that this says that x is related to y if x plus 2y is less than or equal to 5. Now, it's important to remember that these conditions for reflexivity, symmetry, and transitivity are for all types of statements. If it's not enough for these statements about the relations to hold some of the time, they have to hold all of the time in order for us to say the relation has this property. So for instance, this is not reflexive. And you can't necessarily see that the first time you try it, because we've got that, for instance, 0 is certainly related to 0, because 0 plus 2 times 0 is less than or equal to 5, and 1 is related to 1. 1 plus 2 times 1 is less than or equal to 5. So you can find lots of elements that are related to themselves, but you can find some relations that aren't, or some elements that aren't related to themselves. And so as long as you can find a single element that's not related to itself under your relation, that means your relation is not reflexive. We also have that it's not symmetric. We saw that last time by noting that 3 is related to 1, but 1 is not related to 3. All you have to do is come up with one example of an x and a y where x is related to y, but y is not related to x in order to show that your relation is not symmetric. It also turns out to be not transitive. And this one you might have to work on a little bit to figure out, but we could do it, one way to do it would be the following. 3 is related to 1, and 1 is related to 2, because if I plug 1 in for x and 2 in for y, I get 1 plus 2 times 2 less than or equal to 5. That's true, so 1 is related to 2. But 3 is not related to 2. If I put 3 and 2 in there, I get 3 plus 2 times 2 is equal to 7, which is not less than or equal to 5, so we don't get what transitivity would imply. So we have that the relation tilde that we had before actually satisfies none of these conditions on relations, which is fine. We sometimes still want to consider relations like that, but it does give us less to work with if we wanted to prove anything about the relation tilde. Now there's a particular relation that we're going to use very often in algebra that winds up being quite useful for the types of problems that we want to do. So definition 3. Let's let n be a positive integer for two integers x and y. We say that x is congruent to y modulo n if n divides x minus y. So that's saying that x minus y is divisible by n, or another way of saying it is that there exists some q in the integers such that x minus y equals n times q. I don't need these parentheses. If x is congruent to y modulo n, we write x is congruent with three horizontal lines to y mod n. Now this is a slightly complicated notation, but that's because we've actually got three numbers that we have to put into this problem. We've got x, we've got y, we've got n that we need to all work in. Now this notation, the mod n here is to keep track of which relation we're talking about, because we can talk about congruence modulo any positive integer. Congruence modulo 3, congruence modulo 5, etc., and these are all different relations. The three horizontal bars is designed to be reminiscent of equality. Now this relation is not equality, but the notation sort of looks like it, which should make you think that if the people designing this notation have any sense, then this should probably mean that this relation is an equivalence relation. And the good news is that it is, which we'll show and we'll prove here in just a second. But first, some examples to see how this works. We have that 1 is congruent to 5 mod 4. And this is since 4 divides 1 minus 5. And that's because 1 minus 5 is just negative 4, and 4 certainly divides negative 4, because 4 times negative 4 is, or 4 times negative 1 is negative 4. We have that 29 is congruent to 8 mod 7. And the reason we can tell this, I'll use the other description of the divisibility here, is that this is since 29 minus 8 equals 21, which is equal to 7 times 3. So because the difference between 29 and 8 is divisible by 7, that means that 29 is congruent to 8 mod 7. And finally, we could say that 10 is not congruent to 2 mod 6, and that's since 6 does not divide 10 minus 2. 6 does not divide 8. So we have this relation. It's actually fairly straightforward to check whether any two integers are related modulo n. You just take their difference and ask, is this difference divisible by n? So this congruent relationship right here is actually going to be very important to us as we move into algebra and general algebraic structures. So let's get to our first theorem. Therefore, congruence modulo n is an equivalence relation. Now, I'm not necessarily going to go through all the details of the proof here. You can find that in the notes, and you definitely should review that here. I just want to hit the high points and talk about how we think about this theorem, how we go about constructing the argument. So proof. Now, to prove that something is an equivalence relation means that you have to prove three things about it. You have to prove that it's reflexive, that it's symmetric, and that it's transitive. So let's let x, y, and z be integers. First, reflexivity. We have to show that x is related to x, that x is congruent to x modulo n. Well, let's think about this. So x is congruent to x modulo n if and only if n divides x minus x. Since x minus x is equal to 0, which is equal to n times 0, this means that n divides x minus x, so x is congruent to x mod n. Oh, I didn't need to spell out the whole modulo up here. The notation should just be MOD. All right, so that shows reflexivity. If I take any number, it's related to itself because the difference of any number with itself is 0, and 0 is divisible by, well, everything. Let's look at symmetry. So let's suppose that x is congruent to y, mod n. Then that means that there exists some q, some integer q, such that x minus y is equal to n times q. But that means that if I take y minus x, that's exactly the opposite of x minus y. That's what I would get by multiplying x minus y by -1. And therefore, that means that y minus x is equal to n times negative q. I've basically just multiplied -1 on both sides of the equation and gathered the -1 on the right in with the q. And negative q, of course, still belongs to z. And that means that n divides y minus x, which is the condition that means that y is congruent to x mod n. Symmetry is actually quite useful when talking about relations, because if we don't know that an equation is symmetrical, then we have to be very, very careful about what order we write things down in. Okay, is it x is related to y, or y is related to x, etc., etc. Once we have that a relation is symmetric, we don't need to worry about that so much more. So now, from now on, we can just say that, oh, x and y are congruent modulo n, and that means that y and x are congruent modulo n. We don't need to worry about the order anymore, which is going to make this next part a little bit easier also. So let's look at transitivity. Now this proof here has a little trick that's going to wind up being useful to us occasionally, and is not totally obvious. So let's look at that. So let's suppose that x is congruent to y mod n, and y is congruent to z mod n. We want to try to show that x is congruent to z mod n. We want to show that x is congruent to z mod n. Well, that would mean that we would want to know that x minus z is a multiple of n. That x minus z is equal to n times something. Well, x minus z, we don't originally know anything about x minus z. We know about x and y, so we know something about x minus y being a multiple of n, and we know that y and z are related to each other, mod n, but we don't know anything about x and z directly from our hypotheses. But what we can do is we can introduce y's, because we know that x is related to y and y is related to z. So what we can do is to cleverly add 0 in the middle of this relation. So x minus z is equal to x minus y plus y minus z. We haven't actually changed the value of this at all, but now we've got an x minus y, and we've got a y minus z. And we know that x is congruent to y mod n, which means x minus y is equal to n times q for some integer q. And we know that y minus z is equal to n times r for some integer r. And we don't know what it is. But we know that x minus y is equal to nq. We know that y minus z is equal to nr. But now we can factor out n. So we get that x minus z is equal to n times q plus r. And thus, x is congruent to z mod n. All right, so we've shown that a congruence modulo n satisfies reflexivity, symmetry, and transitivity, which means that it is, in fact, an equivalence relation. Now, you'll notice, if you look carefully at the proof in the book and what we've done here, that we've never used the fact that n is positive anywhere throughout here. Remember when we defined congruence modulo n, we said that n should be a positive integer. So you could ask, well, what if we tried defining things using negative integers or even 0? Well, the reason why we don't do it is not because we can't, we certainly can, but that it doesn't get us anything useful. Congruence modulo negative n is exactly the same as congruence modulo n. So if I wanted to say that x and y are equivalent congruent modulo negative 4, that's exactly the same statement as saying that they're congruent modulo 4. And introducing negative moduli in this problem, in this definition, can occasionally cause confusion, and we don't get anything out of it, so we just disallow that. Congruence modulo 0, on the other hand, is perfectly well defined. However, to say that x and y are congruent modulo 0 means that their difference has to be divisible by 0. But the only number that's divisible by 0 is 0 itself, which means that their difference would have to be 0, which means they would have had to be equal to begin with. So congruence modulo 0 is just equality. And we already have a symbol for equality. We already know about that relation, and it's special. So congruence modulo 0 is not useful for us because we already know about that relation. Now, we haven't disallowed congruence modulo 1 here, but congruence modulo 1 is also not super useful. And the reason for that is that everything is congruent modulo 1. If you take any two integers, they are always going to be congruent modulo 1, and therefore to say that x and y are congruent modulo 1 doesn't actually give you any information. So we won't be using that congruence really ever, because it's again not real useful for us. Okay, so that's equivalence relations, and here's our primary equivalence relation other than equality that we're going to be working with pretty often. Now let's switch to the second topic of this lecture, which is partitions. So let's let S be a set as before. A partition of S is a collection of non-empty subsets S1, S2, etc. of S, such that S is the union of all the subsets, and the SIs, these subsets, are pairwise disjoint. Meaning that if I is not equal to J, then SI intersect SJ is the empty set. So another way of saying this, and the way that we usually think about it most often, is the following. In other words, every element of S lies in exactly one SI. So a partition is just breaking up the set into a bunch of pieces where everything lies in exactly one piece and there's no overlap between any of them. So there are lots of examples we can look at. So if S is equal to the set 1, 2, 3, 4, 5, then there are lots and lots of partitions of S. One possible one partition of S is the partition where we take the set 1, 2, then we take the singleton set 3, then we take the set 4, 5. This would be one possible partition of S. Every element of S lies in exactly one of these sets, and there's no overlap, and all the sets together make up the whole S. For another example, if S is equal to Z, one partition of S is given by the following. We could take the set of all even integers and the set of all odd integers. There's a partition of Z. Every integer falls into exactly one of these categories, either even or odd, and nothing falls into both, and we haven't left anything out. So there's a partition. Now, partitions are very useful because they allow us to define equivalence relations. So partitions and equivalence relations are intimately connected with one another. In order to get there, we need another definition coming from equivalence relations, and we'll see how we're going to start building sets out of equivalence relations, which is how we're going to build partitions out of them. So let's see. This is definition 5 in the notes. Let's let S be a set, R a relation on S, given any element of S, the equivalence class of X is the set. We're going to denote it with square bracket X, and it's the set of all Y in S such that X is related to Y. Now, we really, in practice, we only care about these for equivalence relations. In theory, you could define these classes for any relations at all, but we're only going to talk about equivalence classes for equivalence relations. So you can always assume if we're talking about equivalence classes, we're talking about equivalence relations. So the equivalence class of X is the set of all things that are related to X. Or another way of saying it is it's the set of all things that are equivalent to X under the relation R. And because R is an equivalence relation, we can use that language and have it be meaningful. Any element of X is called a representative of the equivalence class of X. Now, in order for this to make sense, we need the result of the following exercise, which is an important one to work out and relies on knowing that we're working with an equivalence relation. If Y is an element of the equivalence class of X, then the equivalence class of Y equals the equivalence class of X. And in fact, this is an if and only if. So to say that that the equivalence class of Y is equal to the equivalence class of X, that's the same thing as saying that Y is in the equivalence class of X, which is another way of saying that X is related to Y. Now, we're not going to go through a proof of this, but I will point out that to prove this, you're trying to prove the equality of two sets up here. And so you can prove this in the in the standard way that we prove that two sets are equal, you can show that the equivalence class of y is contained in the equivalence class of x, and the equivalence class of x is contained in the equivalence class of y. And just to give you a head start on this, if we look at this first part right here, we'll start off by saying something like let z be in the equivalence class of y. And then we think about what does that mean? Well, for z to be in the equivalence class of y, that means that y has to be related to z. So using this description up here, so that means that y is related to z, and then you want to use the fact that y is related to z together with what you already know about x and y to somehow conclude that z is in the equivalence class of x, or in other words, that z is related to x. And so for this, you're going to need symmetry, you're going to need transitivity, etc. So this is something that we're going to use a lot, these equivalence classes. And we're going to, from now on, we're going to take this exercise now as a fact. We're going to use it very often, but don't neglect actually going and proving that. Now, the amazing thing is that equivalence relations generate these sets, these equivalence classes, and these equivalence classes form a partition of the set that you are working with. And in fact, the next theorem shows that equivalence relations and partitions on sets sit in a one-to-one correspondence with each other. For every equivalence relation, there's a partition, and for every partition, there's an equivalence relation related to that. And this interaction goes both ways. So let's look at Theorem 7. Let's let S be a set. So part 1 says that if R is an equivalence relation, then the set of all equivalence classes, equivalent class of X, for all X in R is a partition of S. Now notice that if we actually go and write down all the equivalence classes for all the elements of R, we will have repeated a bunch of these classes, because if X and Y are related to each other, then their equivalence classes are the same. But because we're talking about a set, we just ignore all of the duplicates, and so the result that we get back is just a set of subsets of S. And the claim is that it forms a partition. And part 2 is that if S1, S2, etc. is a partition of S, then, or rather, and R is the relation where X is related to Y if and only if X and Y lie in the same SI, then R is an equivalence relation. And it's not specified in the statement of the theorem, but the equivalence classes you get from the relation in part 2 form a partition by part 1, and those sets are exactly the partition that you started with. So defining an equivalence relation defines a partition. Defining a partition defines an equivalence relation. And if you start on either side of this and go to the other one and go back, then you get back exactly what you started. So let's look at the proof of this also. So part one, so we're assuming that R is an equivalence relation, and we want to show that the set of equivalence classes is a partition of S. Now that means that we need to show two things. Or rather, we wanted to show one thing. We need to show that every element of S belongs to exactly one of these equivalence classes. So let's let X be an S. Now, X is related to X since R is reflexive. It's an equivalence relation, so X has to be related to X. And so X belongs to the equivalence class of X. Every element always belongs to its own equivalence class. All right, so that shows that every element of S belongs to at least one equivalence class, at least one of the equivalence classes, but we need to show that it can't lie in two of them. Now, if X lies in the equivalence class of Y also, then that means that Y is related to X, and hence, I am not using the exercise from last time. If X also belongs to the equivalence class of Y, then that means that the equivalence class of X equals the equivalence class of Y. That's what we did on the last slide. We talked about how the representatives, how any element of an equivalence class is a representative of that class. So if X belongs to any equivalence class, then that equivalence class has to be the equivalence class of X. So thus, X lies in only one equivalence class, namely the equivalence class of X, which is also the equivalence class of Y for any Y that's related to X. So that means that hence, the set of all equivalence classes of X is a partition of S. For part two, I'm not going to write out the proof completely. You can find that in the notes, but I do want to give a bit of a visual intuition here. People have various ways of thinking about algebra, and much of what we do isn't very visual. A lot of the stuff that we do sort of looks purely formal. It looks like we're just dealing with symbols on a page, and there are underlying structures, but they're often not real visually compelling. However, the case of partitions, we can have a visual sort of picture of what's going on. The way I think about equivalence classes is the following. I've got my big set here, and this big blob here is going to represent S. And then to form equivalence classes, I'm just going to break it up into a bunch of different pieces like this. And each one of these pieces represents a different equivalence class. I'm sorry, represents a different subset in the partition. And this is a lot of times how I think about partitions. And so I've split up my my set into a bunch. And so this might be S1, this might be S2, S3, etc., and so forth and so on. And everything in the set lies in exactly one of these regions, ignoring the edges. Nothing lies on the edges. This is just a mental sort of cartoon anyway. So now I want to say that X is related to Y if and only if X and Y both lie in some SI. Okay, so I think about that, and I look at my partition over here, and I think, all right, I want to try and prove that this relation R that I've described in part 2 is reflexive. Well, I know that any element of S has to lie in one of these subsets. That's the point of a partition. So X might lie right there. And if it does, then I know that X lies in S2, and X lies in S2, of course. I can just repeat myself. And so since X and X both lie in S2, that means X has to be related to X by this, by the definition, by the relation that we've defined. All right, so X is related to X. That gives reflexivity. For symmetry, let's suppose that we have X and Y and they're both related to one another. And well, that means that X and Y both lie in some single subset. So we might have this picture. We might have X is in Y, or X and Y both lie in S2. But if X and Y both lie in S2, that means that Y and X both lie in S2. This condition of both lying in the same subset doesn't have any order to it. To say that X lies in S1 and Y lies in S1 is exactly the same as saying Y lies in S1 and X lies in S1. They both mean the same thing. So symmetry holds. And then for transitivity, if X is related to Y, then they both lie in the same subset here. Let's say S2, like we've got it sketched out. But then Y has to be related to Z. So where can Z live? Well, because Y lies in S2, and that's the only subset that Y lies in, that means that Z also has to lie in S2, because if Y is related to Z, they have to lie in the same subset, and the only subset Y belongs to is S2, which means Z also has to be there. But that means that if X is in S2 and Z is in S2, well, that means that X and Z have to be related also. So that means that we have transitivity as well. If X and Y are related, and Y and Z are related, that means they all have to lie in the single unique subset of S that Y belongs to, because it's really the thing connecting them. So that's the idea behind the relationship with equivalence relations and partitions. Now, last thing, let's look at an example where we exhibit this explicitly. So let's consider the relation congruence mod 3. And I want to find the partition of Z, find the partition of Z defined by this relation. So we proved earlier that congruence mod 3 is an equivalence relation. And that means that, based on Theorem 7, it defines a partition of Z. So to see what's going on here, what we can start doing is looking at what the equivalence classes of various elements of Z look like. So let's consider the equivalence class of, let me start with 1 here. Usually we'd want to start with 0, but I want to start with 1 this time. So I want to think about what are all the things that are in the equivalence class of 1. So these are going to be all the things that are congruent to 1 modulo 3. So let me make some notes here. This is all integers y with 1 congruent to y mod 3, which is the same thing as saying that the difference y minus 1 is divisible by 3. Well, first of all, we already know that any number is in its own equivalence relation. Equivalence class, rather. Sorry. Now let's see what other numbers are going to be in the equivalence class of 1. Well, it's going to be anything where the difference between that number and 1 is divisible by 3. So, for instance, 4 is in the equivalence class of 1 because the difference between 1 and 4 is 3, and 3 is divisible by 3, certainly. And then 7. 7 minus 1 is 6, and 6 is divisible by 3. And you can see I can keep getting more elements here by increasing by 3 each time. Every time I go up by 3, I get a new number where the difference between that number and 1 is going to be divisible by 3. And similarly, I can go down. The difference between -2 and 1 is 3, which is divisible by 3. Then -5, -8, -11, so forth and so on. So these are all of the integers where the difference between 1 and that integer is divisible by 3. So we get this big infinite collection of numbers. And so we can say, all right, well, that's taken up a bunch of the numbers, a bunch of the integers, but there are certainly still some that are left. And so if I want to get a new equivalence class, if I want to find some equivalence class that's not the same as the one I have, what I can do is look at the equivalence class of some number that I haven't considered yet, that doesn't lie in the set that I just wrote down. So I could consider the equivalence class of 0, say, because 0 doesn't lie in the previous set. But I can do the same thing. So 0 is equivalent to 3, because 3 minus 0 is 3, which is divisible by 3, certainly. And then 6, 9, 12, 15, etc. And then negative, also, -3, -6, -9, -12. What did I do here? And so here's another set. And then finally I can look for, all right, well, have we gotten everything? No, we haven't. Oh, I noticed that I've left out 2, for instance. So 2 doesn't appear in either of the sets that we have yet. So we could look at that one. And we can follow the same process. So 2, 5, 8, 11, 14, 17 are all in the equivalence class of 2, as well as -1, -4, -7, -10, etc. So these are the 3 equivalence classes that are defined by the equivalence relation congruence modulo 3. Now, you'll notice that we seem to have got all of the numbers here, and in fact we have. We could describe these sets in a slightly different way, which might make it more clear that we've actually got everything. So the equivalence class of 1 is the set of all numbers of the form 3n plus 1, where n is an integer. The equivalence class of 0 is the set of all multiples of 3, where n is an integer. And the equivalence class of 2 is the set of all numbers of the form 3n plus 2, where n is an integer. And you can look at this and convince yourself that every number, every integer, has to lie in one of these three sets. Because a number is either divisible by 3, or it's one more than a number divisible by 3, or it's two more than a number divisible by 3. So any integer lies in exactly one of these sets. The other thing I want to point out here is that these sets have lots of different descriptions, lots of different representatives. Any one of the numbers in one of these sets is a representative of it. So, for instance, the equivalence class of 2 is the same as the equivalence class of 5 under this relation, which is the same as the equivalence class of -4, which is the same as the equivalence class of 17, etc., etc., etc. So these equivalence classes do not have a unique description in terms of, bracket around a representative. But the sets themselves are uniquely determined by the relation that we are working with.